Welcome to this explainer. Every time you ask your phone for directions or type a quick prompt into ChatGPT, an absolutely astonishing stack of linguistics, logic, and mathematics goes to work behind the scenes. It's incredibly easy to take for granted just how effortlessly we speak and understand one another. But teaching a computer to do the exact same thing, well, that is a monumental scientific achievement.
Our whole journey today is based directly on the foundational textbook by Daniel Jurafsky from Stanford University and James H. Martin from the University of Colorado. It is essentially the ultimate blueprint for how we teach computers to communicate. So, we're going to unpack the fascinating story of how artificial intelligence actually learns to process human language.
I'm sorry, Dave. I'm afraid I can't do that. This famous cinematic moment from 2001, A Space Odyssey, perfectly captures the ultimate dream of this technology, a computer that flawlessly understands, parses, and responds to human speech. HAL 9000 wasn't just a machine, right? He was a conversational agent, capable of highly advanced language behavior. He listened, he understood context, he even read lips. And while it's kind of ironic that the ultimate benchmark for conversational AI is a computer that completely goes rogue, HAL represents exactly what computer scientists have spent decades striving to build.
Okay, let's quickly run through our agenda for today. 1. The conversational AI dream. 2. The layers of language. 3. The problem of ambiguity. 4. Solving it with math. And 5. The evolution of AI.
Let's dive right into Section 1, the conversational AI dream, the ultimate goal.
Consider the 1966 ELIZA program. This early bot was basically designed to act like a Rogerian psychotherapist. If a user typed, "You are like my father," ELIZA would just use a super simple pattern matching rule to spit back, "What resemblance do you see?" It successfully tricked humans into thinking it actually understood them, but in reality, ELIZA knew absolutely nothing about the real world. It was just a remarkably clever illusion.
But to move past simple parlor tricks and build something truly robust, a machine needs massive amounts of deeply layered linguistic knowledge. It has to combine automatic speech recognition to physically hear the words with natural language understanding to figure out what those words actually mean in context. Because there's a massive difference between a machine just transcribing your audio and a machine genuinely understanding your intent.
Which brings us to Section 2, the layers of language. Breaking it down.
Think about what your brain does effortlessly in just a fraction of a second. An AI has to compute all of this from scratch, building from basic acoustic sounds all the way up to complex contextual discourse. First up, phonetics. That's recognizing the physical sounds of speech. Second is morphology, breaking words into meaningful parts, like knowing adding an S makes something plural. Third is syntax, the structural rules. The AI has to know that "I'm sorry, Dave" makes sense, but "sorry, I'm Dave" means something entirely different. Fourth, semantics, the literal meaning of the words. Fifth, pragmatics, the intent. When Dave says, "Open the doors," it's a strict command, it's not a casual question. And finally, discourse, the larger context. If you ask your phone how many states were in the US that year, it needs discourse knowledge to remember exactly what that year refers to from, say, 3 sentences ago.
That naturally leads us to Section 3, the problem of ambiguity, multiple meanings.
Consider this tiny forward sentence. "I made her duck." For us, the meaning is probably perfectly clear depending on the context of our conversation. But for a computer, it is an absolute processing nightmare. A computer parsing this raw text sees multiple competing structural possibilities all at once.
Seriously, those 4 tiny words contain morphological, syntactic, and semantic ambiguities resulting in at least 5 completely different and quite hilarious meanings. Does duck mean a bird or the physical action of lowering your head? That's a part of speech ambiguity. Does make mean to cook, to create, or to force an action? That's a semantic ambiguity. Depending on exactly how the machine classifies these words, the sentence could mean "I cooked waterfowl for her," or "I caused her to quickly lower her head," or even "I waved my magic wand and turned her into a waterfowl."
So how do we fix this? Let's look at Section 4, solving it with math. Filtering ambiguity.
Historically, researchers actually tackled this through 2 intensely competing paradigms. You had the symbolic camp, which relied on strict, programmed logical rules. And then you had the stochastic camp, which relied on probabilities and statistics. The symbolic approach literally tried to program every single grammar rule and logic tree into the machine. But human language is just way too unpredictable and messy for rigid rules. So the stochastic approach, which uses data to determine the mathematical probability of a meaning, became the clear winner.
Ultimately, nearly all speech processing today reframes every language ambiguity as a mathematical search. Instead of getting completely bogged down in strict grammar, the underlying formula is actually pretty simple. Just look at massive amounts of previous data, roll the digital dice, and calculate the most probable meaning. State machines handle the word parts, but when the machine faces a tough choice, like deciding if duck is a bird or an action, it relies entirely on statistical probability.
And that brings us to our final part, Section 5, the evolution of AI, a generational climb.
We're essentially looking at an accelerating technological explosion here, starting from Alan Turing's early theories of computation in the 1940s, going straight through to the modern era of machine learning. What really turbocharged AI in the early 2000s was the availability of huge collections of texts, like the Penn Tree Bank. This provided the immense amount of annotated training data that those probabilistic and machine learning models absolutely needed to get incredibly accurate at guessing our intent.
Now this brings us to a really fascinating psychological reality. Think about it for a second. Do you ever find yourself saying please and thank you to Siri or Alexa? A famous 1996 study by Reeves and Noss found that people naturally extend human politeness to computers. We treat them as team members, and we just expect them to understand our needs. We are psychologically wired to treat a talking machine as a social entity, regardless of whether it uses simple ELIZA rules or massively advanced neural networks.
So, I want to leave you with this final thought drawn from Alan Turing's legacy to ponder. If a machine perfectly mimics understanding through math and probabilities, does the illusion of intelligence just become its own reality? Turing believed that if a machine could successfully fool us into thinking it understood language, well, that was proof enough of intelligence. As these probabilistic models become flawlessly woven into our daily lives, maybe the line between computing statistics and true understanding doesn't matter nearly as much as we thought. Thanks so much for joining me on this explainer, and keep questioning the technology around you.